All right, beautiful human beings of Math HL. This is Mr. Ropke, and today we're looking at chapter 15, sections G and H. They both have to do with lines and how they might intersect or perhaps might not. So let's give it a go. This is a quick snippet from the book. It says that vector equations of two intersecting lines can be solved simultaneously. What do I mean about solving them simultaneously? Specifically, if two lines are going to intersect, the x-coordinate of one needs to equal the x-coordinate of the other. The y-coordinates need to be equal. And if we're dealing with 3 dimensions, then the z-coordinates need to be equal too. That's the plan of attack here. So we're going to open up with something relatively simple. We're in 2 dimensions here. We have some random quadrilateral ABCD. So I might start off by drawing just some random ugly thing. ABCD. All right, well, it's a pretty crappy picture because if I look a little carefully here, I might notice that the direction vector AB is 4, 1, and CD is -8, -2. Clearly, CD's direction vector is just -2 times AB's. So AB should be parallel to CD. And over here, -8, 32 is also proportional to -3, 12. So actually BC and AD should be parallel as well. So rather than drawing this ridiculous looking thing, I should have a parallelogram. Next says use vector methods to find the coordinates of A, B, C, and D. I'm going to do the work for A. The work for B, C, and D is identical, just with different numbers. So here's what I know. I know that vector AB and vector AD, they intersect someplace, specifically at point A. So if they intersect at point A, that means that the x-coordinate for AB should be equal to the x-coordinate for AD. Similarly, the y-coordinate for AB should be equal to the y-coordinate for AD. That gives me a system of equations that I can solve. And the result will be u equals 1/3 and r equals 0. I then take those values and I substitute them back and like checking my work to make sure that I get the same value both times. This is going to get me A is the x value. Over here, if I put in 0 for r, I'm going to get 2. And over here, if I put in 1/3 for u, I will also get 2. So the x value is definitely 2. And similarly, if I put in r 0 and u 1/3, I'm going to get 5 as the y value. I need to get the same value for in both the left side and the right side for them to intersect at that point. If I get different values, that means that I solved my system incorrectly. So you do the exact same process to figure out the coordinates for B, C, and D. I've filled them in the top right. So now we can move on here to little letter b, write down the vectors AC and DB. So using the coordinates that we just worked out, AC is 12, 20, and DB is 20, -12. Hence, we can find the magnitude. So magnitude of AC, you can kind of tell based on the 12 and the 20 involved in both of them that that's going to be equal to the magnitude of DB, which is going to be the square root of squaring and adding 544. Next, we want to find out what AC dotted with DB is. Since this is in 2D, you can kind of cheat and look at that. That indicates a line with a slope of 20/12. This indicates a line with a slope of -12/20. They're opposite reciprocals, so we know they're going to be perpendicular, but just to practice using the dot product so that we can do this in 3 dimensions in the future, we're going to do 12, 20, dotted with 20, -12. Okay, obviously, that's going to equal 0. So what do those answers tell us about the quadrilateral? Well, these two diagonals being congruent here, that tells me that it has to be a parallelogram. And these two diagonals being perpendicular to each other, tells me that it has to be a rhombus. And if I have a quadrilateral that is both a parallelogram and a rhombus, what does that make it?
A square! Yeah! Yes! So good. So good.
Okay, so line classification in 2 and 3 dimensions. If we have two lines interacting with each other, how can that occur? In 2D, we know they're either going to intersect, in which case they have a unique solution. There's one and only one solution. They could be parallel, in which case there are no solutions because they don't intersect. Or they could be, we're going to use the word coincident to indicate that they are just really the same line or two lines taking up the exact same space, in which case there are infinitely many solutions. You've all seen this before. Now we need to extend this into 3 dimensions. So in 3D, we might still have two lines that are within the same plane in 2D space. Those lines are then called coplanar. If two lines are coplanar, then they could either intersect or be parallel or be coincident, because if they're coplanar, then it's really just the two-dimensional situation. But lines might not intersect, and they also might not be coplanar. So I've got a picture of a cube over here. This line and this line, they're clearly not going to intersect, but they're also not in the same plane. And I don't think you would look at those and say, oh yeah, those two lines are parallel. So the word we're going to use for that situation is skew. Now, when we want to work out the angle between lines, we know that if the lines are parallel, then the angle between them is going to be 0 degrees, 0 radians, whatever. If the angles are intersecting, then we can calculate what their angle is using the dot product, as you saw earlier. If they are skew, we still pretend that they're going to intersect and calculate the angle if they did, right? So if we took this red line here and we translated it through space to be there, those two red lines are clearly parallel. They are coplanar. And then we could calculate the angle between the red line and the blue line. Similarly, we could translate the blue line forward in space and calculate the angle there. Obviously, it's the same. And we can do this with any skew lines that we want to. So now we're going to answer some questions. But before I do, I want to call attention to some issues I have with the textbook. Okay, so we're reading chapter 15, section H. So far, so good. 2D lines, great. Get to page 454. What is going on here? We're talking about row operations here, augmented matrices. Like, what are these words? Echelon form. Most of you don't know what any of this means, and you don't need to. My recommendation to the majority of the people viewing this video is to just not read this page, okay? I will do some examples here using the mathematics that you already know, solving systems of equations with elimination. And we can use this method in 2D and in 3D, no problem. You don't need to worry about these matrices. I think if you're planning on studying further mathematics beyond HL, or also the IB Further Mathematics course, you're going to run into linear algebra in the future, in which case understanding row operations will be very important. So this is certainly the language that mathematicians use to solve systems of equations once they get, especially once they get above 3. So I like it. I think it's easier. I think it's faster than using the elimination method, but in the interest of not confusing you and just getting you to be able to solve problems quickly and efficiently in the HL math context, I'm going to say don't worry about matrices, okay? All right, so looking at this one, we've got a system of two equations with two variables. Great. Letter A, use row operations to reduce this system. We don't need to do that. The IB will never ask you to do that. It's unnecessary for us to use that to solve B and C. We can do B and C just fine. So for what value for k are there infinitely many solutions? Well, I mean, think about this. If you rewrite that first equation as 6x minus 2y equals 16, then we notice that it has the exact same form as the equation below, same coefficients for x and y. So there will be infinitely many solutions when the equations are the same. So that means k is to equal 16. Okay. What form do the infinite number of solutions have? So that is not really immediately obvious from the way this question is phrased. We are going to be interested in writing down the general solutions to systems of equations, and they're going to be in parametric form. So similar to how we saw that a point on a line, its x and y value and z value could be determined by some parameter. We're going to do the same thing here. And this is how we're going to do it. If we write down the equation that we have, 6x minus 2y equals 16. We're going to make a choice here. We're either going to solve for x or solve for y. It doesn't matter which one we do, so I'll do both just to show you. We could get x in this case would be equal to 16 plus 2y all divided by 6. You could simplify that if you wanted to. If I solved it for y, then I would get y is equal to 3x minus 8. So for the form of my infinite solutions, one of them would be 16 plus 2t, or whatever letter you want to use for your parameter. I'll use t here, divided by 6t, or t, comma, 3t minus 8. So what that says is if I choose a value for t, it will determine the coordinates of x and y according to the rules I've just written down. In the example on the left, if I chose t is equal to 0, now like t is not really the same t for both of these, but I'll get the exact same points out of both of them. So just to show you what I mean, let's choose over here on the left. Let's say I set t equal to 0. So if t was equal to 0, then my x coordinate would be just 16 over 6, and my y coordinate would be 0. That coordinate also exists over here on the left, on the right, but on the right, that means t would have to be equal to 16, 16 over 6. My x value is therefore 16 over 6, and my y value, I multiply 16 over 6 by 3, I get 16 over 2, which is 8, and 8 minus 8 is 0. Any x and y combo that I get on the left, I can get the same xy combo on the right. They're just attached to like different t values. So either one of these in the boxes is an acceptable general form. This generally is seen as confusing by a lot of students the first time that they see it, but it's actually really easy. What you need to be careful of with problems like this is you might do your own work and get an answer, and then you might check it with a friend, or you might check it with answers in the back of a textbook or on a website or something like that, and you'll find that they give a completely different looking answer. Your work might still be correct. You just chose to solve for a different variable. You chose to set a different variable equal to your parameter. Usually the official IB mark schemes say at least, they'll give a general form and then they'll say or equivalent. And that's a clue to you that, oh, maybe there's another way I could have done this. But I don't know if that's always the case. And I've had a lot of students in the past ask me questions like, what did I do wrong? And the answer is you did nothing wrong. You just wrote your answer totally differently. It's a pain for me, by the way, grading exams when everyone does it differently. I hate these problems for that reason. But anyway. So now we're going to do letter C. When does the system have no solutions? Well, clearly, if k equals any other number besides 16, then this system's going to have no solution because it's the same values on the left but different constants on the right. And what does that mean geometrically? Well, if there's no solution, we know that the two lines are parallel. So I've got two equations here, and I've got m's flying around. Let's go. I want to find, they tell us that it has a unique solution, so we want to find that. And the way we're going to do that is by solving this thing with elimination, as we've done many times in our lives before. I'm going to multiply the top equation by 2, and multiply the bottom equation by m, and then I'm going to start eliminating things. So I can subtract my two equations to eliminate the x terms, and that'll give me 4 minus m squared times y is equal to 12 minus 6m. And I can solve for y now. So my y coordinate must be 12 minus 6m divided by 4 minus m squared. And this will work out as long as m is not plus or minus 2. If m is plus or minus 2, then I'm dividing by 0. So like those are my no-no values. So m will have a unique solution as long as that's not the case. All right, so now I'll do letter B, find a unique solution. I suppose first we should simplify that expression for y. We can cancel out the 2 minus m's. So we get y is equal to 6 divided by m plus 2. And if you substitute that back into your original equations and figure out what x is, you find out it's actually the exact same thing. So that's our unique solution, as long as m is not 2 and m is not negative 2. Even though it looks like m equals 2 would work here, the problem with that, again, is if we put m equals 2 into this system, then we end up getting two equations that are the same, which therefore will not have a unique solution. But as long as m is not 2 or negative 2, we'll have a unique solution. And by the way, it kind of makes sense for the x and y coordinates to be the same if we think about this system here. There's kind of a symmetry happening, right? They both got a 6 over here. The coefficients of x and y switch from one equation to the other, so I'm not surprised to see the same coordinates for x and y in my unique solution. Now, as for the other two cases, so what's happening when m is positive 2 and what's happening when m is negative 2? Well, we just discussed what happened when m was 2. When m is equal to 2, we have two lines that are exactly the same, so that means that we're going to have coincident lines. And when m is negative 2, I mean, a good guess would be to say that there's going to be no solution, but let's just write it out, that we're going to have negative 2x plus 2y is 6, and then 2x minus 2y is 6, but we can rewrite that second one as negative 2x plus 2y equals negative 6. And now, yeah, clearly there's going to be no solution there. If we, subtract one equation from the other, we're going to end up with 0 being equal to 12 or some nonsense. So in that case, there will be no solution. If you're uncertain what's going on here, pop on over to Desmos and graph the system and play around with it. You can graph the equations as they are written. You'll make a slider for the value of m, so we can change that to see how things change in the graph. I've got my solution point here, 6 over m plus 2, comma 6 over m plus 2. And I also have 1.5, 1.5, because when m was equal to 2, something interesting should happen. So we can just set m in motion and see how things change here. And sure enough, when m is equal to, oh, wow, that was good. I'm keeping this take. When m is equal to negative 2, my lines are parallel, so there we have no solution. And then when m is equal to exactly 2, that's when the lines are coincident. And as m gets super, super, super big, we can see that the solution point just gets closer and closer and closer to the origin, right? If m was to be super big, both of these expressions here would both be essentially 0. Their limit would be 0. So anyway, that's what's happening here. Fun, fun, fun. Lots in front of us here. I'm only going to do 4 of these. I'm going to do one example of parallel, one of intersecting, one of coincident, and one of skew, just so that you can see all 4 of these situations. First, we'll do letter A. So the first thing I want to check for each of these is the direction vectors of each line. Because if I find out that the direction vectors are scalar multiples of each other, then I will know that the lines are either parallel or coincident. If the direction vectors are not scalar multiples, then they will either intersect in one place or they will be skew and never intersect. So I can kind of narrow these the options down in this fashion. So for the first one, for letter A, my two direction vectors are going to be 2, -1, and 1. And that is not going to be equal to any scalar multiple of 3, -1, 2. So therefore, these two lines are not parallel, and they're certainly not coincident either. So now we're going to search for an intersection. We said earlier that that means that the x values for both lines have to be the same, and the y values, and the z values. So we've got 3 equations here, but only 2 variables. So we're free to choose any pair of lines or any pair of coordinates and solve that system. So it doesn't matter which ones we choose. Let's say we were to choose these two. You can take a minute and do the work if you want to, but the solution to those two gives us s equals 1 and t equals 0. So then I would go back into all 3 coordinates, x and y and z, and see if those work for all 3 of them. In this case, they do. In this case, our x value is just going to be 1, our y value is just going to be 2, and our z value is just going to be 3. And that's true on both the left-hand side and the right-hand side. Since this worked out for all 3 coordinates, these lines are going to intersect at the point 1, 2, 3. If it had not worked for all 3 of the equations, I mean, look, it better work for y and z, right? Because we solved that system to get s equals 1 and t equals 0. So if it doesn't work there, that means that we made a mistake in solving the system. But it's not a guarantee that it's going to work for x. Okay, so that's if it doesn't work for x, that's an indication that the lines are actually skew. The directions ask us to find the angle between the lines. That's just our dot product friend again. So we'd be solving cosine of theta is going to be equal to the dot product between these two, which is going to be 6 plus 1 plus 2. So it's going to be 9. And then we're going to have on the bottom, it's the square root of 6 times the square root of 14. Grab your calculator. Theta is going to be equal to, I think, 0.190 radians. So now we'll do a second one. So we'll do letter B. First, I look at the direction vectors. 2, -12, 12. Not a scalar multiple of 4. That should be 4, positive 3, -1. Sorry about that. Regardless, not a scalar multiple either way. So these lines are not parallel, and they're not coincident. They either intersect or they're skew. I just did an example where they intersect, so spoiler alert, these are going to be skew. I write down my 3 equations again, one for x, y, and z. I pick 2 of them to solve. It doesn't matter which 2. If we were to choose the bottom 2 again, then we would get a mu value of 5/2, and we would get a lambda value of -5/8. We could substitute those back in for y and z, and we'll find out that, you know, again, as I said before, it's going to work for both of those. They'll both give us a y value of 19/2, and they'll both give us a z value of -7/2. But if we put in lambda equals -5/8, we're going to get an x value of 4. And if we put in mu equals 5/2, we're going to get an x value of 7. And those two are not equal to each other. So that's our indication that these 2 lines are skew. So let's do letter C now. C, we've got direction vectors 6, 8, and 2, and that is exactly 2 times 3, 4, 1. So that tells me that these two lines are either parallel or coincident. So now we're just going to find out whether they have an intersection point or not. So again, pick any pair of equations. It doesn't matter which ones you choose here. You're going to find that you're going to get no solution. That indicates to us that these two lines are parallel, but not coincident. Therefore, the angle is, of course, 0 degrees. I think I forgot to do the angle for part B. Part B's angle was 1.09. 1.09 radians. This is 0 degrees. That's, of course, 0 radians. Finally, to do one that is coincident, we can look at letter G. Again, the direction vectors, 2, -1, 3, that's certainly a scalar multiple of -4, 2, -6. So it's either parallel or coincident. I write my system of 3 equations. Choose any 2 of them that you want, and you will find that those 2 have infinitely many solutions, indicating to us that these 2 lines are coincident. We'll say again that the angle between them is 0. All right, so that's the end of this section. Once again, no matrices required for this course. If you're good at matrices, then I really encourage you to use them. If you're not good at matrices, feel free to learn them. I think it's a really nice bit of mathematics that you're likely to encounter in the future anyhow, and I think it actually does make a lot of this work faster and less sloppy, especially when we get into the sections that are coming up next. But again, as you'll see in the future videos, totally unnecessary. So if you're feeling overwhelmed at this point, I don't want you to think you need to learn even more bonus mathematics, as much as I do love them.
And you were like, a square! Oh my god, a round of applause. Some advanced maths to know. Anyway.